Hey guys, it's your boy Chili here. Welcome back to C++ multi-threading. Today we're gonna be changing direction a little bit. We're gonna look at a thread pool that can handle generic tasks. Whatever you throw at it, it's gonna get the job done. So up until now, we've had a collection of workers. And these workers can all do one very specific task. They're all queued to a very specific task. So now imagine that we're actually using this in some kind of system, right? Let's say our machine has 4 cores. Okay, and we've got a bunch of different kinds of tasks that we need to do. It's different processing, different code. So we would need a different worker collection for each one of those kinds of tasks. If we have 4 kinds of tasks, A, B, C, D, we would need a pool of workers for each different kind of task. And we would put, probably around 4 workers in each one of those pools because we want to make sure that we can utilize the full potential of our CPU. We like to distribute the load of the work equally among all of our cores. So, okay, this seems reasonable, right? Now, let's look at some problems with that. First problem, let's say in our program at any given time, only one task is going to be processed. So we're only going to be doing, let's say task A, and then later we might be doing task C. So when we're doing task A, these threads are going to be working. They're going to be executing, running on our cores, but all the other threads, they're just sitting around with their thumb up their butt. And you might say, well, that's fine. They're not utilizing any CPU slice. So what's the harm? But while they don't use any CPU slice when they're sleeping, they're still consuming memory. Every thread has at least its own stack, right? And that's going to grab a chunk of memory. So yeah, I mean, we've got, maybe in this scenario here, we've got 12 threads at any given time that are just there, but they're not strictly necessary. We're retaining them because we don't want to recreate threads every time we need to execute, task C or whatever. But now let's expand the problem. Let's say, okay, now our CPU doesn't have 4 cores. It has 16 cores, which isn't a crazy amount of cores in today's day and age. 16 cores, and let's say we have, 100 different task types. So now we have to create bespoke worker objects for each one of those 100 task types, which is annoying. And let's say each one of those task types, we want to fully utilize the CPU for any of them. So they all have to have 16 threads. 16 times 100 is 1,600 threads. We can measure the memory usage now in the gigabyte range for how much space. And if we're only ever having, 1 or maybe 2 of those tasks active at a time, the vast majority of that memory is just wasted. I don't even know. There's probably like a limit to how many threads you can spawn in a single process. I don't know what that number is. But anyways, you can see here that the situation isn't great. We have to have all these bespoke, collections of different threads for each different kind of task that we have. Now, what if we had a thread type G for gangsta, or generic if you like? Either is fine. And this thread type can actually handle any kind of processing thrown at it, as long as it's of the type task. So we can wrap in our task here, we can wrap some maybe lambda or other function in a task, throw it at this thread pool, and it will execute that on one of the threads. So then we only really need to retain, in this case, we only need 4 threads. And no matter how many different kinds of tasks we have, doesn't matter, because these 4 threads can do anything. That's a beautiful situation. And there's other reasons why having this generic pool is great. Another is oversubscription. So let's say, again, in our scenario here, we give 4 threads for each task because we want them to run on our 4 cores. Why don't we give the task 8 threads? There's no point. Only 4 can be running at a given time. If we use 8, we're doing something called oversubscribing. And when you oversubscribe, you're not using any more cores. You can still only use 4 at a time, but it's constantly, CPU, the operating system constantly has to switch between your threads, and that adds extra overhead. So it's bad. You only want to run about the same amount of threads as you have cores maximum. So we have 4 for each task because we have 4 cores. But now let's say we're running 3 tasks simultaneously. Oh no. Now we're running 12 threads on 4 cores. We're oversubscribed 3x and we're not efficient. And again, if you have a fixed thread pool that runs all your things, you can solve that problem as well. And we'll probably look at that in a future video. But today, let's just focus on creating a thread pool that can handle generic tasks. So in the code base here, I'm going to basically ignore most of these. I might reuse the task and constants again. I haven't decided yet. We'll figure it out as we go. But unfortunately, I did name the name task is already used, so that's annoying. But anyways, let's just jam everything into main.cpp because I'm lazy. And because I already used the name task, let's create a namespace and we'll just call it TK for task. Yeah. I don't know. And we'll put everything in TK and then we won't have a naming collision with our existing task. So we're going to need a class for our thread pool. We could call it like task runner or whatever. I don't know. I just call it thread pool. Who cares? Now, what is the interface like this going to look like? So it's going to class task. Don't do that. Yeah. Okay. Don't put it none. Just leave me alone. Okay. So there's going to be a function to run a task, I think. It seems all right. So let's go void run. Now, there's lots of questions here. Do we take a task in by value or do we take one in by reference? I'm not sure. Usually if I'm not sure, I'm just going to resort to value and we'll figure it out as we go along. So run a task and this will execute a task somehow. Is there anything else we need in our thread pool? Right now, I don't think so, but I mean, we're probably going to need more, right? Private. Okay, so we got a std vector std thread, or should it be a J thread? We'll use a J thread just to start off with, and then we'll think about it. But it's probably the J thread, right? Yeah, okay. So we have a std vector of threads, and now I'm just thinking to myself here. I haven't planned any of this out, so I'm running blind a little bit. But I mean, we're probably going to want a mechanism to figure out when a task has completed. Because if we got a bunch of tasks, if we split up a workload into a bunch of tasks, and then if we want to gather the results at the end, we have to know that all the tasks are done before we can start gathering the results. There are a bunch of ways we could do this that are very sophisticated. I don't want to do them today because I want to just keep it simple right now. So we're just going to write a little function to check if there are any running tasks on the thread pool. This is not a good solution to the problem, but it will do for now and we'll make it better in the future. Bool is running tasks. All right, so we've got a vector of threads. Some of these threads could be running tasks. Other threads might not be running tasks. And we get a new task to run. We have to give it to one of the threads that is not currently working on stuff. So we need a way of signaling that our threads are indicating which threads are working and which threads are not working. Worker, we'll just call it a worker again. Seems fair enough. Okay, private. Now, well, I'm thinking here, I would like to signal whether flag whether each worker is busy or not. So we'll use std atomic bool busy. Bool is busy const. No, I'm not gonna put no except in here. And return busy. Okay. So we have a worker, it could be busy. Now our vector worker, workers. Each worker is going to have a std thread, std j thread, just a thread. Let's put underscores for private members. Let's just do that while we're at it for our new system here. All right, so this allows us to implement the isRunning tasks. Std all of, I got ranges. Yeah, all of, let me see here, workers underscore const auto and w dot is busy. Let's go none of workers is busy. Is none of a thing? Return. Bah. Oh, didn't complain. Hasn't IntelliSense. Okay, none of is a thing. Good. So if none of our workers are busy, wait a minute. If any of our workers is busy, then we are running tasks. So our worker is going to need a kernel, functions, data, void, kernel. We'll just call this one run kernel. We shouldn't have to pass anything into the run kernel function, but maybe we will or something. Okay, so kernel is going to have a bunch of logic to be able to, it's going to need signaling so that this thread can get a task when it is submitted to the thread pool. It's going to need some signaling to wake it up so it can execute the task that it's received. But it also needs signaling to know when it's time to die. And JThread has a nice little mechanism for that called stop token, but it's a little funky to use. It's good, but yeah, so like example in here, JThread runs with F. So if we make F take in a stop token as its first parameter, it will receive that when a JThread is created with F, automatically get that. And then we can call request. So then if we destroy the JThread, it'll automatically call request stop. So what you can do with the stop token is you can check it to see whether a stop was requested from the outside. And if so, return from your kernel function. But what happens if you're waiting on a different condition? You can't check the stop token. If someone flags it, you won't be able to see it. So you need a mechanism to be able to signal your condition variable when you get a stop request. And it so happens that there is a cool thing that you can do. So there's a std condition variable any, which is like just a more powerful version of condition variable. So our kernel should take in std stop token st. All right, and we're going to need some more stuff here. We're going to need a std condition variable any. That's our C include condition variable. There we go. And we're going to need our std mutex as usual, as you do. Maybe we'll move the thread to be first thing that is going to be constructed. We'll see. Can we do this all in a constructor? I'm just thinking, do we actually need anything for this constructor? I'm rethinking it right now. I'm like, maybe we don't need anything. So the idea is that we pass the stop token in when we wait on our condition variable. So let's do while true. We are going to start off by just waiting on our condition variable. So we should perhaps lock our mutex when we get in here. Should we lock it Okay, so obviously we need our constructor to launch our thread with our kernel. So yeah, we need a constructor. Worker thread underscore worker run kernel. Like that. All right, so that should be fine, right? Now, when we get in here, let's create a std. What is it called? Unique lock, maybe? Unique block. Yeah. LK on our memtx. Good. So far, so good. And then we're going to do CV wait. Okay, here we go. All right, it wasn't the constructor of the any, it's the wait function that takes in the stop token. There you go. So yeah, I was surprised because, you know, CPP reference is usually pretty on point with their new stuff. So I'm like, why isn't it in there? It's not the constructor, it's the wait. Yeah, there it is. Okay, there we go. As usual, the world wasn't crazy. I was just being dumb. Good. That's what I expect and what I like to see. So we wait with our lock, stop token, and our predicate. So what kinds of stuff do we want to store? So we can signal death with the stop token, so we don't need a shared piece of memory for that. But we have to also signal whether we are giving a task to our worker. So we can signal that, and here's how we have to think about things. What is a task? What is a man? It's just a function, right? It's just a function that we can call. Std function? No takers for that? Okay. Include functional. How about that? And we have to unify, because this is generic, our worker has to be able to run all these different tasks. So they have to have a generic interface. So they will just have, for starting off, we'll just have a function that takes no parameters and returns nothing. In the future, I'd like to expand this, but we'll have to think about that one. That's a thinker right there. So for right now, task is actually just an alias for a std function. And let's just go task. So when we start off, the task is empty. So we can do something like this. Return task dot. Damn it. Does std function not have like a operator bool? Oh, that's what we want probably. Task. So if there is something, task, not just return task, right? This pointer to task. There you go. And that'll convert to bool. I don't know if it likes it. Let me think here. Bam. Maybe it likes it. Yeah. So that'll be true if the function actually holds a function and it's not empty. If it's empty, it returns false. And there you go. We have our condition set up for waking up with additional condition for stop tokenry. And we wait, and all is good. And then if we wake up, we get to this point. Mutex is locked, and we should do if stop token dot stop requested. So if someone requested a stop, return. Right? Just bail out. If that's not the case, then that means that we must have work to do, because that's the only other condition that can allow us to stop waiting on the condition. Task. Just execute the task. once we're done executing the task, we want to empty the task. So that means that task is equal to default constructed task. Busy is equal to false. You know, I'm not being very consistent in my naming here. I think that's it. No. We need a function that the thread pool can call to give the worker some. Again, we can just call it run task. And what is this going to do? To run a task, do we need to take the mutex? I mean, it seems like taking the mutex is the safest bet, but is it a pessimization? Do I technically need to take the mutex? We will only call this function if this atomic busy is false, which means this should be empty. Now we can talk about the the memory reordering and stuff like that, but if this thing has a memory order, a strict memory ordering about it, it can't reorder operations past here. So I'm thinking we don't even need to take the mutex. Am I crazy? It seems very odd to me to have a mutex, but it's not actually protecting any data. But you do need the mutex in order to use the condition variable. That's the funny thing. I'm just gonna like be a little monka s in here. I'm not gonna take the mutex. And if anyone has a concrete explanation as to why I must take it, I'd love to hear it in the comments. But I'm just gonna be a little risky. We'll do a little risky business. So when we run a task, right, so we just do task is equal to std move task. We set the internal task. I'm even going to do it like this. I'm going to use the signal, the atomic signal here, also in the condition variable as the wake up variable. Busy is equal to true cv dot notify. I'm not sure which one of these is likely to be more performant, but there's only ever one, so I guess we'll just do that. All right. There you go. So we've got this thing, but we're not taking the mutex before we modify this shared memory, because we're hoping that this atomic bool is going to provide the synchronization point to make it technically correct. We'll just see. We'll see, A, if it works properly, B, if anyone yells at me in the comments, and that'll be fine. All right, so right now, we need to implement the actual running of a task on here. Now, I should point out at this point here, this thread pool only is meant to be used by one thread. So if we want to make it usable by multiple threads, we'll have to add extra protection. Like for example, for this, we'd have to take a mutex before we check any of these, because someone could add tasks after we've checked a particular thread. You know what I'm saying? So if we wanted thread pool to be thread safe so that multiple threads could submit tasks, then we'd need extra protection, but we're just saying thread pool is to be used by a single thread alone to launch tasks onto multiple worker threads. Okay, so to run a task, what we do is we do std find std ranges find workers for which it is true that worker, for which it is false that worker is busy. So if I is not equal to workers.end, then we have a non-busy worker. So let's give him task. Were I pointer to run std move task. Yeah. Otherwise, all of our workers are busy, and we're going to change this logic and make it a lot better in the future. But for right now, we're going to do the simplest thing possible, which is, okay, now I got to think here. Now I got to think a little bit, because I was going to say that the simplest thing possible is to push another worker. But if that push triggers a growth of the vector and has to copy these value objects, is this thing copyable? Is a thread, no, it'll move them. Is a thread movable? Yeah. Is an atomic bool movable? Yes. Is a condition variable movable? I don't know. Is a mutex movable? I don't think so. So I think these two might not be movable, in which case we don't want to trigger that from, we don't want to do that. So we could make, there's a bunch of ways we could do this, but I think the simplest is just to make our workers std unique pointer worker. And this might even give us some advantages in the future if we make workers, if we make polymorphic workers. But for right now, this just enables our vector to grow without messing up our workers. Now the sad part of this is that now we can't just do our projection into our workers because they're not values anymore, they're pointers. So we have to do it in a slightly less sexy way, which is const w, so that's a pointer to a worker. W pointer to is busy. So find a worker that is not busy. Right, so find needs a value. So we want to find the first one where busy is false. We use find if. Oh, find if only needs a predicate. Okay, never mind. So we just do this. Yeah, so we need to dereference the iterator. That'll give us the pointer, and then we use that to run this thing. Then, if there are no workers that aren't busy, we should do workers dot push back std make unique worker. Wait a minute. What's your problem? What is your freaking problem? Push. All right, it's fine. It just had a little hiccup. Push a worker back, and then workers dot back. The one at the back is the one that is guaranteed to be free. So run our task. I don't know why the compiler is being angry about this, but might have to look at it again. But anyways, these ones here, std any of worker, w pointer to is busy, and that should be that. You should just pass in the pointer to run the member function, but that didn't fix the problem. And I did a little digging, and what I found was basically when you're doing this with a member function, not just a free function, but a member function, you put your pointer to the member function, and then you put your pointer to the instance into JThread like this. But with the stock with the stop token in there, JThread wants to call a function that takes a stop token and this, which is not, so it gets confused. The template metaprogramming logic in there is either flawed or it's impossible to do the differentiation necessary. So what you can either do is you can bind the instance to the member function to create a free function that you pass the JThread. Or the other thing you can do is don't take in a stop token in your kernel, get that stop token out from the JThread object itself. So we'll try this one. So how does that work? Well, this stays the same. This no longer takes a stop token. We lock the mutex. We go auto st is equal to thread dot get stop token. And then Bob's your uncle. All right, so that's the other thing we could try. Please just build. Yay, we did it. So that's actually a very funky and trippy thing that can trip you up. Like, you know, I like to use these cool mechanisms that they put into the standard library instead of rolling my own thing. But sometimes there's like some gotchas and then it's like, maybe I should have just rolled my own damn thing. But once I get it to work, I'm happy. So I'm a happy boy. Anyways, so this is probably working. What we're going to do is we're just going to erase all this stuff. It still exists. It's in the Git history. We're fine. I don't know what POPL is supposed to mean. Get rid of that. So let's just run like a test task in here just to make sure that stuff is working. So tk thread pool. A task is just a std function. So what we can do is we could do pool dot run. Wrong. There we go. Std cout. And let's run another one. Low. There. So we're just going to run 2 tasks on our thread pool just to make sure that it doesn't completely shit the bed. Okay, so it didn't print anything out. What if it signals the stop token before it actually started its work? And then it would do stop request and it would return immediately. Interesting. So the current behavior allows it maybe to cancel. So what we can do here, very simple. While pool dot is running tasks, here's an easy test. Std this thread sleep for 10 milliseconds. Oh no. Oh no, we need the using namespace chronoliterals. And then we can sleep for, let's just do like 16 milliseconds. Yeah. Okay. Yeah. So we're just going to sleep and we're going to wait. Wait until we're not running tasks anymore. Now let's see if this shows stuff up on the screen. All right, no. It just keeps running. So apparently we have a problem where tasks don't finish. Perhaps they don't even start. Oh, right. Oh, dies of cringe. Okay. So this is like the reason why you put an underscore on your private member variables so you don't get confused with like locals and parameters. But then I just didn't put the... Okay, well, joy of joys. That's worked. And like I thought before, I don't think this is necessary. But again, I'd be very open to being proven wrong there. High low. Okay. Now we shouldn't have to wait for this. Low. Interesting. What if I run it again? Exception thrown. Okay, I think I figured out how my dumbass done screwed this up. And it's a tricky one. But basically, let's just look at it again. Looking at the stack here, we can see that basically mutex, when we try to lock a mutex, we get a problem. And in my mind, we get a data access violation. In my mind, that's one of two things. Either we've got some kind of an invalid this pointer, and so it's not getting the memory that it's looking at and doesn't have a mutex in it. Or it could be that the mutex was already destroyed, went out of scope or something like that. Now, here's the thing. The mutex was already destroyed because we create these things. When we create a worker, we create its members in order. First the thread, then these ones. When we destroy it, these are destroyed in order. So first the task, then the mutex, then the condition variable. And the last thing that is destroyed is the thread, and that is what sends the signal to, which will wake this condition variable up and do. But the problem is the condition variable and the mutex are already destroyed at that point. So that is an insane order of initialization. Truly insane. So the last thing that should be created is the thread. When the thread is created, all these things will have already existed. And then when we destroy our pool, we call the destructor of each worker. The first thing it does is it sends the signal and it blocks on this thread. Then this stuff finishes its job. Then once this exits, destruction can continue on, and all these other things that are necessary inside of the kernel will get destroyed. But they will not get destroyed while the kernel is still running, which would be very scary. Okay, so now that we're not doing anything incredibly retarded. Okay, so yeah, and I'm going to continue on with my instinct that I don't need a mutex here. There we go. So now it works, and works, and works. And yeah, we have a thread pool. We can run any task that we throw at it. Just make a lambda on the spot, throw it to the thread pool, and it'll execute it on a different thread. Very nice. And I'm like 90% sure that we don't need to lock the mutex here, at least in terms of undefined behavior. It is not undefined behavior to do it like this. But again, if I'm missing something, then let me know in the comments. Just be sure to support your assertions. Don't just say, no, you're wrong without any kind of backing there. That's just dumb. In the future, I'd like to expand on this, and we're gonna have a lot of different things that we can add to this. Task will not just be an alias for a std function. There's gonna be more that goes into here, and lots of good stuff. But this is a decent start. This is dece, as they say. So I'm gonna leave it at that. Hope you enjoyed the video. If you did, please click the like button. Helps a lot. And I will see you again with some more C++ multithreading.